Well, thank you to Ernesto for his world presentation. Thank you to the organizers for the invitation to be here. It's a great pleasure and a great honor to be in Samuel Gitler Center of the CIMAT staff. And thanks to all of you for being here. Well, this picture is Samuel Gitler in one of his famous talks. The subject is not completely related to what is written in the blackboard. What doesn't matter is Samuel talking about classification space and universal bundles and so on and so forth. I want to talk about work in progress with Walter Ferrer and Álvaro Ritatore from Universidad de la República in Uruguay. And since most of the audience is not so familiar with schemes, let me try to make a brief introduction with a more familiar language. Maybe, okay. So let's assume you have a topological group. And then, of course, you have the actions of groups. So you have an associativity for the multiplication, you have the neutron element, and there is another diagram, which I didn't write, which expresses the fact that you have an inverse map. Of course, the requirement is that all these maps are continuous. If the group is equipped with a structure sheaf, say for the topological group, you always have the sheaf of continuous functions. Functions to the reals. Then, of course, every time that you apply, take continuous functions in an open set on U, you can take the preimage on G times G, and then the preimage on G times G times G, and there is a map backward. So contravariant map. And then, so you have dual diagrams, which also should commute. In particular, which is the case important for us, if G is the spectrum of a ring. So suppose you have the spectrum of a ring, you have the prime ideas on the ring, you provide it with some topological structure called the Zariski topology, and you ask for, assuming you have a group structure on that, you ask for these diagrams to commute and for corresponding diagrams of regular functions to commute. For instance, you could take G to be the linear group, which can be seen as the group of the zeros of this polynomial, determinant equal 1. Or you could think of A as being, oh, I didn't write, sorry. You could think of A to be the ring of polynomials in n squared variables, and then modeled by determinant of xi y times y minus 1. So this could be the ring A, and then all the prime ideas corresponding to this will give you the scheme associated to the group SLNK. And close points, meaning maximal prime ideas, correspond to close points, the usual points that you are used to on SLNK.
This one is GLN,
No,
no?
determinant 1. Ah, you're right, sorry. Yes, sorry. That one is GLN, so I don't need that. Sorry, yes, thank you. So any Lie group can be think of as a particular affine scheme. Well, not really affine, as a particular group scheme. So assuming you have an affine, and then in particular the commutative diagrams associated to the duals, to the structure sheaf, will give you some diagram So as I was saying, you can take functions on U. If you're in a topological group, you just take continuous functions. It could be a manifold, and you take C-infinity functions. It could be an analytical manifold, then you take holomorphic functions. Or if you are thinking of it as a scheme, then you take regular functions on an open set. There is a map on the other way to the structure sheaf on G times G of the inverse map, of the inverse of U, etc. But if you think of U as the whole space, then you recover here A. Here you recover A times A times A times A times A. And there are maps associated to this. This is called co-multiplication. Co-multiplication times identity. Identity times co-multiplication. This diagram should commute. There is another one associated to the identity, so you have the co-identity, and there is a co-inverse called the, I don't remember the name. Antipode, yes, thank you, the antipode. Now, if you are in an affine scheme, it is the case that the commutativity of these diagrams assures the commutativity on any open set. So it's enough to have the commutativity there. You don't need to check it on all other open sets, because there is a basis for the topology given by open sets of the form, well, the usual notation is df, which is the special places where some function is not zero, and the regular functions on this kind of sets are just localizations at f. And since this is true, this commutes. Once you localize it on if, it commutes again, and then this is a basis of the topology, so you get it for free. So for affine spaces, that's enough. And the diagrams are not, this is only one of the diagrams, you have three, and this gives you a structure of a Hopf algebra. Okay? So I'll just start with an affine group schemes. You end up with an Hopf algebra, and it's actually equivalent. So you always have a Hopf algebra. These are two of the diagrams. This is the one I have written there. There's another one for the co-unit, and I didn't write the antipode map. Okay. So again, if you have an affine group schemes and finite dimensional vector space over K, you can think about representations of the group on this vector space. To have a representation of G on V is to have a map from G times V to V, which satisfies the usual rules of an action of a group. And you ask it to be linear. So this is just the associativity of the action, and this is the identity, the action of the identity element. It's doing nothing. Okay. It is equivalent to give a map from G to GLV. It's exactly the same, which is the usual way to think about representations. Now, the category of representations form a category. You can tensor them, you can take direct sums, etc., etc. They form a category. This category is a neutral Tanakian category. Or another way, it's a rigid abelian category, which means that you have tensor products. You have a neutral element, which is the trivial representation. You always have the trivial representation. Okay. Given two affine group schemes, the representations are equivalent as categories, as Tanakian categories, if and only if the affine group schemes are isomorphic. Okay, so this is really giving you the whole classification of the groups, of the affine groups, and any neutral Tanakian category is equivalent to the representation of some affine group schemes. So this is called Tanakian theorem. So for affine groups, it's wonderful, affine group schemes. Now, what's happened if you are working with something which is not an affine group? For instance, an abelian scheme, or more generally, an anti-affine group scheme. Anti-affine means that the global sections of G are only the constants. This is the case for abelian schemes. So if the global sections are only the constants, or if you have an abelian schemes, the only representations for this. So if you have a vector space, you have GLV, which is an affine variety. The affine variety I wrote first, with a determinant different from 0. And the only maps as the schemes, the only regular maps from A to GLV are constant maps. Since this should be a homomorphism of groups, has to be the identity map. So there are no representations other than the trivial ones for abelian schemes, for abelian groups. It's different to what happens in infinity case, because we are, for instance, taking holomorphic functions from a compact manifold to C. There are no holomorphic functions from a compact manifold to C except the constants. It's not the case for S1. There are a lot of morphisms, infinity morphisms from S1 to GLB, all the characters, for instance. Here you don't have. Okay? So what to do in that case? And that's the subject of this talk. So there is a famous theorem, Chevalier, Renaud, Brion. If J is of finite type over K, finite type is nothing more sophisticated than what you know. A scheme is of finite type means that G is of finite type if its closed points form an algebraic variety. So an affine, even if it's not affine. So a group of finite type may have some nilpotent elements in the structure sheaf, but anyway, the closed points with its reduced structure corresponds to a variety. So it's what you have in mind: GLB, SLB, SP, something, whatever. In that case, for this kind of schemes defined over a field, there exists the smallest normal subgroup, which is called GF, such that the quotient is proper. GF is affine and connected, that's why it's called GF. And the formation of the affine part commutes with the extension of scalars. So if you have a field which is bigger than the original one, then it's just the rational points. Okay? The K rational points. Moreover, if the field is perfect and G is smooth, so again, it may be not smooth if you have some nilpotent elements in the structure sheaf. But if you avoid that, if you take the reduced structure, then it's smooth. And in that case, GF is also smooth. Actually, it's an if and only if. GF is smooth if and only if G is smooth. And there is an exact sequence like that. G to the quotient, which is a proper scheme, and GF. This is left exact. Okay. Well, let me continue and then I explain what it means. G to the quotient is flat, surjective, and quasi-compact. These are very big words. The point is that any time that you have a scheme, you can think of the scheme as a sheaf in some Grothendieck topology, right? You just take the functor of points points. So meaning the ohms from something to G. And in some topologies, this is achieved. Actually, you could take the Zariski topology, a tal topology, flat topology, whatever topology, and this will be achieved. So this condition of being left exact means that this is an exact, left exact sequence of shifts. Surjectivity is subjectivity, as you know it. Flat is a kind of technical condition, meaning that the Hilbert polynomial of the fibers are always the same, meaning that the fibers are, in this case, all the fibers are isomorphic to GF. So it's flat for free. And quasi-compact means that if you think of this as a sheaf on the quasi-compact topology of Grothendieck, then this is exact. Okay? Remember, a sheaf is a sequence of sheaves is exact doesn't mean that for any open set it has to be exact. It means that if you have something here, there is a smaller open set where it comes from somewhere, from some section here. And that's precisely the condition, but now open sets means open on the quasi-compact topology. Okay? Quasi-compact morphisms are morphisms from X to Y. You call it quasi-compact if you can cover Y with the open sets, Zariski open sets, in such a way that the preimage of each one of them is quasi-compact. Quasi-compact is, for the young people, just compact, except that we old people used to call compact when it was also Hausdorff. It need not to be Hausdorff. It's just the usual definition of compactness that you are used to, but we old people use compact only when it is Hausdorff. And this is not Hausdorff because Zariski topology is never Hausdorff, except if you are in a discrete set of points. Okay. So far, so good? Okay. And again, here, asking of quasi-compactity of this Q is essentially trivial because any affine scheme is quasi-compact. So if the fibers are quasi-compact, and then you take an affine open set here, the fiber will be automatically quasi-compact. They mean the preimage, the open set on G, which is the preimage, will be automatically quasi-compact because the fibers are quasi-compact, the open set is quasi-compact. So, okay. Moreover, if G is connected, there was no reason for G to be connected at this point. If G is connected, the quotient is an abelian variety, just an abelian variety.
If G is an abelian variety, then GF is
just 1 point.
Yeah, true.
Yes, yes. Or maybe, yeah, yes. You maybe have an isogeny and then GF is just a finite set of points, nothing more than that. But since we are thinking of GF as the smallest normal subgroup, then it will be really a point and this is the identity. Okay? Okay.
So wait, can you give us an example to have in mind where GF is not trivial?
Actually, any extension of an abelian by whatever affine scheme that you want. Yes, these are the examples. And these are the examples that we have in mind. Now, that comes the definition. A sequence of morphisms of group schemes is called a short exact sequence of group schemes if, when you think of it as a short sequence of shifts in the quasi-compact topology, it is exact. So this is left exact, Q quasi-compact, and faithfully flat. Exactly the situation before. Okay? Then the Chevalier decomposition on any connected group scheme of finite type is an exact sequence of group schemes. Wonderful. Now take a group scheme H and schemes G and A. we have in mind H and affine group schemes. Doesn't need to be the case in this definition. G is some extension of A by H, and A could be an abelian group scheme, but in this moment it's not important. You have an action of H in G, and an H invariant morphism from G to A, for instance, with the trivial action of H in A. Then this map is a torsor if it is quasi-compact and faithfully flat, and G times G over A is isomorphic to H cross G. Okay? So it's the notion of a principal bundle translated into this language. So if you have a principal bundle, that is a torsor. But now it's a principal bundle on the quasi-compact topology. That's all what I am saying. Okay? So in any short subsequence of group schemes, Q is an n-torsor. By definition, for me, a short subsequence means an extension of Q by n in the quasi-compact topology, and it will be automatically a torsor, so a principal bundle, which is more or less to expect because the fibers are all isomorphic to n, so it's essentially nothing. If Q is abelian and n is affine, we will call it an affine extension of the abelian group Q. Now you take an abelian extension, an affine extension of an abelian variety, then G is automatically quasi-compact, which is what I was saying, because Q is not only quasi-compact, Q is actually affine. The fibers are affine. If H is of finite type, well, I say already that. H is of finite type if and only if G is of finite type. Well, it's not only quasi-compact. Affine extensions form a category. So you have a morphism for affine extensions. In our case, we are thinking the identity over A. So are affine extensions of the same abelian variety. Okay, that's important. Affine extensions of the same abelian variety form a category. And the map should be the identity. It's not any map. It's not an isotopy. It's the identity. Okay? Now, so anytime you have an affine extension, as I say, G is a quasi-compact group. We are, first of all, interested in proving the converse. If you have a quasi-compact group, it should be in some affine extension. There should be a affine extension realizing this quasi-compact group. Maybe I should point out to this. These maps are it's affine. Phi and phi restricted to H are affine because Q and Q prime are affine. Okay? So if you take an open set, a fine open set here, the preimage on G prime is affine, and then you take the preimage of any affine here. Well, this is a technical thing, but the expert already know what I mean. Okay? You take in principle, some open affine cover here, and the preimage should be affine. So you take precisely the open cover formed by the preimage of this. That's it. Okay. So the first proposition is that if you have a sequence of affine extensions of an abelian variety, an inverse systems, there is a limit for this system because the morphisms are affine. So you have a limit for G alphas, you have a limit for H alphas. Moreover, this limit is affine. So you have an affine extension. It is just a universal property of the inverse limit. It's nothing more than that. In particular, if these are Chevalier composition and H is minimal among the affine groups so that the quotient is abelian, proper. Sorry. So, if these are Chevalier decompositions for these abelian, for these groups, say of finite type, where you have Chevalier decompositions, Then, okay. Then these H alphas are minimal, and this H is again minimal. It's a minimal affine group, so that the quotient is proper. So this H is minimal, and any affine extension with H central can be produced as an inverse limit. You need the central because you need to be sure that there is a quotient by H alpha. Okay? And here I am not asking H to be of finite type or whatever. It's just affine. Then now comes the first important result. Any connected group scheme fits into a pro-algebraic affine extension. Pro-algebraic just means inverse limit. We didn't find a better word to express that at the moment. We will change this definition, but it doesn't matter. And the idea goes to go back to Perrin. He proved that any connected group schemes is an inverse limit of some groups, which are just the quotient by subgroups. So these quotients are of finite type. These K alphas are subgroups of G, affine connected closed subgroup schemes. So any connected group schemes can be written in this way as a limit. Since these are of finite type, then you have Chevalier decomposition for those. So you can write this. Now the problem is that these Q alpha depend on alpha. They are not the same abelian variety. Nevertheless, there exists a limit, so you will get something like 1 to some H, to some G, and some Q. But since these Q alphas are not necessarily the same, this Q may not be an abelian variety, may have some nilpotence. There is no reason for it to have a reduced structure. Nevertheless, there is always a map to some abelian when you kill the nilpotent. And then you have to work out, you have to first to check that there is a map from G alphas to H, which is not trivial because it is an inverse limit, not a direct limit. So you have to lift the maps from G alpha to Q, and then you just follow this, take the kernel, this is the new G H alphas, and then you are done. And you can take the limit there. So it's not completely trivial. There is some work to be done there. Okay. So as I was saying, there is an affine extension killing the nilpotent. And now it comes the representation theory. What should be a representation theory for this kind of extensions? So first, consider two vector bundles over the abelian variety A. We are going to consider maps from E to E prime, which are not just the normal maps of vector bundles over some scheme. Usually, the maps from vector bundles over some variety you ask them to commute like this. Here you have an extra structure because A is an abelian variety. So in particular, it's a group. So we are asking that there is some multiplication by something here, which makes this diagram commute. And this something, so you are multiplying by some element down below, so that this diagram commute, and you call that A the degree of this map. Okay? So if it's of degree A if this diagram commutes. And of course, you ask the restriction to the fibers to be linear. But it's not over the same fiber, just pushing the fibers to a different point. And you called about the homomorphism from E to E prime of degree A. If you take two morphisms, then the composition is about A plus B. You can take the sum of homomorphisms if and only if they are of the same degree, because you cannot shift by something and then by something different, and it doesn't make any sense. So they have to be of the same degree. And the usual homomorphisms of vector bundles are of degree 0. Okay, you are respecting the fibers. Okay. The composition is as you expect it to be. You call a bundle homogeneous if you translate by something and they take the pullback is isomorphic to A. Okay? So these are homogeneous bundles. Then you have the category of homogeneous vector bundles with morphisms of degree 0. And we call the homogeneous vector bundles graded, the category of homogeneous vector bundles with all possible degrees. Okay? All these morphisms. That one is an abelian category, monoidal, rigid, subcategory of that one. And it's actually a neutral. HBA is actually a neutral, abelian, monoidal, rigid subcategory. So in particular, this is always a Tannakian category. And you can think of this as the category of representations from a affine group scheme. It's not so surprising as we will see. So given a homogeneous vector bundle, we denote this, the fused abelian monoidal rigid subcategory generated by A. And of course, you also consider the one generated with all degrees, morphism of all degrees. You put that GR over there. Okay. And the homomorphism from E to F of every degree has a structure of homogeneous vector bundles. Okay? So you have something like an internal home in this category. And then, of course, you take the ones of degree 0, which are the usual endomorphism from E to E. There you have the automorphism, those who are invertible. And here you also have those who are invertible, and you have just a map like this. And remarkable, this is an affine extension, okay, of A. If you take a vector bundle over A, then this is a group, and this is an affine subgroup of this, and form an affine extension. And then you can guess what the representation theory will be. It's just a morphism of affine extensions from this extension to this particular one. Okay? That will be a representation for us. It's equivalent, as it was in the affine case, to have an action of G on A of some degree. Actually, not only of some degrees. Let me be more specific. So you have an action of G on E. G will be an extension of A. So you have a projection from from G to A. E will be a bundle over A, so you have a projection. And here you have the multiplication map. And this kind of actions will be, it's the same as having this representation. Okay? Okay, so this is what I say. You asked it to be linear on the fibers. Amorphism of representation is what you can guess it has to be. And the category of representations is a category. And then, again, a lemma given an affine extensions and a representation, finite dimensional representation of H, which is an affine group schemes. So this is just a vector space, and a representation of the affine extension, which is a bundle, an homogeneous bundle on A. First of all, you can form this quotient, G times B mod H, exists and is a representation of this, even if H is not of finite type. So this is, it took us a while to, not to figure out that we needed something like that, but to figure out how to prove it. There is a similar result on Mumford, but he used H of finite type. But if you look carefully at his proof, he's going back to SGA 3 or something, and there is a proof with a finite type. This is just quasi-compact descent. It's nothing more than that. So this is quasi-compact descent. It exists always. So in particular, the vector bundle you started with, which is this representation, can be recovered using only the fiber at 0, which is a vector bundle. Okay, I thought. So let me make a stop here. How much time do I have, Ernesto? Or someone else? Doesn't matter. Well, I will see. It doesn't matter. Let me make a stop here. What we want to say, what we prove, is that this category of representations of G given by homogeneous vector bundles over A with a G action it satisfies something like Tanaka theorem. So there is two groups have the same, have equivalent representation categories if and only if they are isomorphic as extensions of A, okay? And any category which resembles a representation category in this sense is coming from some group. Now, the first part is not so surprising, because if you have an extension, what you have is this. So you have this. H is an affine group scheme, so H can be recovered by the representation of H, the usual ones, the vector spaces classifying representations of H. And this extension can be characterized by some element in H1, let me put quasi-compact of A with coefficients in H. This is just one element here because this classifies extensions of A by H. So if you know the extension and you know the representation, you know everything. You can say this extension, this particular extension. So if you know this, you recover H, and then you know the class. Now, recovering the class is the difficult part. That's why we need to do something. But I mean, philosophically, it's not much more than that. And we are not going to recover the class explicitly. Okay. So let me give this lemma. If you have a closed subextension, this is a classical lemma, which is true in the affine case. So if you have an extension, a closed subextension of the original one, then there is a module for this, a representation of S, and an homogeneous subline bundle of E such that G prime is the stabilizer of L. This is exactly the same result for usual representations. You have a subgroup of something, then there is a representation of the big group whose stabilizer is the smallest one. That's it. So it's essentially the same proof. You take the fiber of this E, this is the fiber, on H, on 0. This is a final representation of H. Then you take a one-dimensional subspace here whose stabilizer is H prime, and then you just go back, and that's it. Now, this is Tanaka. There is a forgetful functor from representations to homogeneous vector bundle with disgraded homomorphisms. You take just the bundle, and the representations of degree 0 are a wide subcategory, just the same objects, but the morphism just of degree 0, restrict to the usual forgetful functor on degree 0. A natural transformation is what it should be, as a family of morphisms, making this diagram commute. And in particular, you have some lambda on E of some degree and lambda F on F of some degree. Because of the commutativity of the diagram, A and B should be the same. Okay? So everybody's on the same. If you have a natural transformation, everybody's on the same degree. It better be, because you want this natural transformation to represent an element of the group. An element of the group is above a precise element on the abelian variety, taking the projection. So it better be on the same. Well, it doesn't, it's a blah blah, doesn't matter. Then you take the endomorphisms. So all the natural transformation could satisfy these two properties. They are compatible with tensor product, and the identity acts as it's supposed to be, trivially. Then you take the invertible ones. You can take the invertible ones when restricted to the subcategory generated by a fixed representation. You have an extension. These are the ones of degree 0. These are the usual ones. And since you have this for every subcategory, full subcategory generated by any E, you can go to the inverse limit and you get an extension like this, where you make it an inverse system, saying that D prime is bigger than or equal to A if and only if A is the sum of A prime with something. Okay. Then the theorem, given any pro-algebraic affine extensions, these natural maps is an isomorphism. Okay? But this is very similar to the proof of the linear and of the Tanaka case in the affine group schemes. And again, if you have some category with some forgetful functor, with fully faithful functor from the category to the homogeneous vector bundles, or with every possible degree, such that for any pair, these homomorphisms here is a vector, subvector bundle, homogeneous subvector bundle. And when you take the ones that go to degree 0, these form an abelian rigid monoidal category, then this is a representation category of something. Again, it's just the same lines as the linear proof of the Tanaka theorem. It's essentially the same. Just follow the pattern. With this adaptation that we have done, it's very easy. It's very natural. Now is maybe time for a small stop to see the time. What time do you have? Yes, okay, wonderful. So there is only one thing left so far. For the affines case, you have on one side Tanaka theorem saying that every representation is some kind of very specific rigid category, which is a Tanakian category, neutral, rigid, abelian category, and the converse. Any rigid, neutral, abelian category is the representation theory of something. But you also have that the sheaves produce some Hopf algebra. We want to produce some analog of a Hopf algebra in this case. It won't be a Hopf algebra, because if you get a Hopf algebra, you get an affine scheme, and you don't want that. But it's very closely related. So if you have two maps from X to Z and from Y to Z, and quasi-coherent sheaves on X and Y, respectively, then we define this curly tensor product locally as the quasi-coherent sheaf given by this tensor product, where U is some affine scheme, affine open set on X, B is some affine open set of Y, W some affine open set on Z. F of U is given by M twiddle because F was quasi-coherent. The same for G is N twiddle for some N, and then you just take the product over C and twiddle. In particular, the sheaf structure of the product, of the fiber product, is precisely this. So we're just generalizing a classical notion. Given an affine extension, this, what I said here is classical. If you have an affine extension, then you can take the push forward of the structure sheaf, which would be an OA algebra whose spectrum is precisely G. I mean, that was known to Grothendieck and everybody since SGA3 or something. But now, the commutativity of this diagram. That's because Q is affine. Yes, exactly. That's nothing more. Q is affine, so this is no abstract nonsense. The commutativity of this diagram induces a map from OG to the structure shift here, which is what we call this twiddle product. And if you apply Q star, so let me go back. So this is from OG to M lower star of this twiddle product. And if you apply Q star, then you get from Q star of OG, which is H, to this, which is S star of H twiddle H, where S is the multiplication map here, by choice notation, sorry. And the inversion morphism gives you a map from here, and then again you get when you apply Q, you get a map from H to the opposite of H, which is the antipode map, or will play the role of antipode. And the commutativity of this unit will give you something which is closely related to a co-unit. So you essentially have co-multiplication, co-unit, and antipode, which is not exactly what it was in the fine case. So the diagonal gives you this co-multiplication. So this satisfies a commutative relation similar to those of a Hopf algebra, which are still written there. Sorry, it's the other way around. Are still there. So here's one of them. And a tuple like this will be if H is an OA algebra which is flat as a module, then you have this co-multiplication, this antipode, and then also the multiplication, because you need an algebra after all. And you have the co-unit, and this will be called a Hopf shift. And the proposition is that if you have a Hopf shift, then G, which is the spectrum of H, is a group scheme. Actually, it's an affine, an affine extension of the abelian variety. H0 is a Hopf algebra. H, which is the spectrum of H0, is an affine group scheme. And you have an extension like that, an affine extension. If you have an action of G on X, an isomorphism of OG times A modules from here to there is a G linearization of F if it satisfies some cocycle condition. If you have an affine extension, then a shift representation of S is essentially an homogeneous OA module with a linearization. And the category of representations of the extensions is equivalent to the category of finite rank. Oh, I forgot to. Sorry. The category of representations of S is equivalent to the category of H modules, or H co-modules actually. So rep S is equivalent to H co-modules. So we recover so far everything, at least this aspect of what's known for the affine group schemes. Okay? And then are, of course, a lot of questions about Hopf algebras and Hopf co-modules, which we don't know yet. We are working on that. Well, that's it. Thank you very much.
So this notion of Hopf sheaf, it's slightly different from saying a Hopf algebra object in sheaves of OA modules, right? It's because the operations on A are involved.
Involved is, yeah, but
There's push forwards under.
it's slightly different, but in any case, the point is that the fibers are Hopf algebras. Yes. But as you say, it involves the multiplication on the base, so it's slightly different, but it's the only difference. I have just one remark. This, without knowing that before, and this is in the same spirit as some lecture I heard some couple of years ago by Bernardo Ríve, saying that you will not expect the representation of something to be in the same category as, I mean, you should expect the representation of something to be in the same category to the object you are representing. So you're representing affine extensions, the representation should be some affine extension, which is this vector, homogeneous vector bundles. You say that at some point. Well, thank you.